in question 1 you have three variables actually. X is a function of t as t squared, and y is a function of t as that, t squared minus 4t. So basically x and y are functions of t. Each of x and y is a function of t. Okay. To understand the parametric equations of curve, so basically we call two equations, x is a function of t, y is a function of t. We call two equations parametric equations. Okay. The parametric equations define a curve. The curve is called the parametric curve. To understand the parametric curve, you just remember one thing. Every value of t is called a parameter actually. By parameter, we mean t can take any number on some closed interval or on some interval. T is, I said, a parameter. Okay, t is a parameter. It means t can take any number. Later on, I'm going to make more comments. Okay. I told you you only need to understand one thing. Okay. Every value of t determines a point on the curve. I will make some more comments on that. I will copy this question to PowerPoint. Then I'm going to make some more comments. Okay. On the screen you have parametric equations. X is a function of t as t squared. Y is a function of t as t squared minus 4t. Okay. I told you each value of t determines a point on the curve. So now let's try to evaluate. Now let's try to get some points for the t values. So now let's say t value of -2, t value of 1, t value of 0, t value of 1, and t value of 2. Okay. We'll get these points one by one. Now the solution. Again, I want to repeat, each value of t determines a point on the curve. You have many choices of the values of t. Okay, you can each value of t determines a point. Many t values will determine many points. In general, you connect many points, you have a curve. This curve is called the graph of the parametric equations, or we can just call it a parametric curve. Okay, now let's try to get some points. So how about we start from t value of 0. Okay, t value of 0 will give you x coordinate, x value of 0, so 0 squared, right? 0 squared is equal to 0, and the y value, you plug 0 into that equation. T value is 0, so the value of y when t value is 0 is equal to 0 as well, right? 0. And so we'll try to get all the 4 points. Okay, t value of 1. The next point we are going to get is the point for t value of 1. T value of 1 will give you x value of 1 squared, so which is 1, right? And the y value is computed using 1 squared minus 4 times 1. T value is 1. I think x value is 1, y value, I meant 1 squared minus that. One squared minus 4 times 1. I believe this number is equal to 3, so correct me if you see anything wrong. Okay.
Wouldn't it be -3?
Yeah, -3. So sorry about that. So the point for t value of 1 is the point with x coordinate of 1 and the y coordinate of -3. And the t value of 0 will give you a point with x coordinate of 0 and the y coordinate of 0, right? Again, I want to repeat my point. It's actually the key to understand a parametric curve. Each value of t determines a point on the parametric curve. You have many choices of the values of t, so you have many points, right? You connect many points. You have a curve. The curve is called the parametric curve. Actually, it's a little bit tedious to get to compute all the points. I believe I have all the points in the notes. We just get all the points from the notes. Okay. This is the curve, the parametric equations we are talking about. Okay. A t value of 0 will give you x coordinate of 0, y coordinate of 0, and t value of 1 will give you x value of 1 and y value of -3, and so on. Okay. T value of -1 will give you x value of 1, y value of 5. Again, I'm not going to go over all the points, but each value of t determines a point on the graph. Now, for instance, this is the point determined by t value of 0. 1, 5 is the point determined by t value of -1, right? 4, 12, you look at the mouse cursor. This is the point determined by t value of -2. Okay. And likewise, this is the point determined by t value of 2. Okay. A little bit of comment on parametric curve. If we treat the parametric curve, now look at question 2. Actually, it's in question 2. You look at question 2. The two parametric equations are the same. Okay. In question 2, the difference is that there is a restriction on t. T is between -2 and 2. T is greater than or equal to -2 and less than or equal to 2. Right? If that's the case, if t is defined on some interval, then we can treat where's the curve? Then we can treat the curve as a directed curve. We can treat the curve as a direction. Okay. T is from -2 to 2. The direction will take this point as the initial point. This is the point for t value of -2, right? This is the point for t value of 2. So later on the curve is going to be, you connect all the points. You have the curve. You follow the mouse cursor. Okay. The curve is going to be something like this. Probably I have that on the next screen. And then we can treat this parametric curve as a direction. The initial point of the directed curve. Can I say it's a directed curve? We can treat this point as the initial point. We can treat this point as the terminal point. By that we mean we treat the curve as the curve so directed from this point, following the curve, okay, to this point. Again, I want to repeat the point I was trying to make is that a parametric curve on some closed interval can be treated as a directed curve, having a direction. Alright, any questions? Should not be too hard. We have seen the first curve, we have seen the second curve. Again, the difference between these two is in question 2 there's a restriction on t. We treat t as a parameter value from -2 to 2. So because many terms are new, I'm going to repeat the terms. We call t a parameter, right? It means t can take any value on some interval, or any value, or any real number. Okay. Now we look at the third curve. Now question 3, I mean. Okay. We look at question 3. I'm going to copy question 3 to PowerPoint. should be simple to understand the meaning that, should be simple to get all the points for the t values of -2, -1, 0, up to 4. Should be simple to compute this point. Now, for instance, to get the point for the t value of 0, you plug t value of 0 into the two equations. I just get you 1 point. Okay, so t value of 0. I'm not going to do the question in details. Okay, t value of 0 will give you the point with x coordinate of 0. I think t value of 0 will give you y value of 1 and the y coordinate of 1. So the point with x coordinate of 0 and the y coordinate of 1 is on the curve. Again, you have many choices of t values. Correspondingly, you have a curve. Right? I will show you the computer sketch of the curve. T squared minus 2t, t plus 1. I think I have this curve in here. Okay. If you use the website, so decimals.com, it can sketch the any parametric curve. The syntax is something like this. So that's the function defining x, the function of t defining x, right? The highlighted this part is the function defining y. So by that we mean the parametric equation is x equals t squared minus 2t and y equals t plus 1, right? And t is ranging from -2 to 2. We also treat this one as the curve with a direction. Okay. I think t value of 2 will give you that point. T value of -2 will give you that point. Right. So the curve is treated as a directed curve from this point to that point. So basically the direction is going, that's the initial point, going along the curve, so that's the terminal point. I think I got it right. Again, on the screen, you'll have the parametric curve defined by the parametric equations in question number 3. Okay. Simple enough. Again, to save time, I'm not going to get all the points. You just remember every value of t on the interval defines a point on the curve, and then you connect all the points, you have the curve. Simple. Now question 4, I want you to kind of remember this parametric curve. I don't know you bother to do that or not, but I'm going to show you the computer sketch very shortly. Okay. Now let's try to get a few particular points. It's not the detailed solution, so maybe I'm going to write the solution key. Okay, the solution key. Now let's get the point for t value of 0. T value of 0. If t value is 0, then x value is cos of 0, t value is 0, right? The whole thing cubed. And then t value of 0 will give you the y value of sine of 0, the whole thing cubed. Which means t value of 0 will give you the point cos of 0 is 1, sine of 0 is equal to 0. So t value of 0 will give you the point on the curve having the x coordinate of 1 and the y coordinate of 0. So does that make sense? Again, you need the trig values. It depends. In some cases, you do need the direction. In some cases, you don't. You do not have to indicate the direction on the curve. Again, I'm trying to say t value of 0 determines a point with x coordinate of 0 and y coordinate of x coordinate of 1 and y coordinate of 0. Okay, it's kind of the point with x coordinate of 1 and y coordinate of 0 is on the graph. Now let's get another point, the point when t value is half pi. Okay, t value of half pi. If you want, you can try to get all the points for all the t values. Now I'm trying to tell you t value of half pi will give you x value of cos of half pi, now the whole thing cubed, right? And the y value of sine of half pi, the whole thing cubed. Cos of half pi is equal to 0. Sine of half pi is equal to 1. Now let's recall some famous trig values. So this will give you the point with x coordinate of 0 and y coordinate of 1. Right? By that we mean the point with x coordinate of 0 and y coordinate of 1 is on the graph. So that's 1, 0. I think that's 0, 1, right? And likewise, these 2 points are also on the curve. So that's the point with x coordinate of -1 and y coordinate of 0. And this point has x coordinate of 0 and y coordinate of -1, right? But now we are not going to get a circle, so because of the thing cubed. I will show you the computer sketch. Okay. In the parametric equations, we do not have a restriction on t. By that we mean t can take any real number. I will show you the computer sketch for the curve. I think I have it somewhere. I will zoom in. Okay. You see, that's the point we identified. That's another point we identified. In this case, how about if I have to give a restriction on t, I will make t go from 0 to 2 pi. So this curve has a shape, so something like this. It's called asteroid. Okay, I will show the name in the notes. Okay. Do I have the name in the notes? Yeah, so probably it's somewhere in later chapters. That's the parametric curve. In this one, you just have the general a value. In the question we did has the a value of 1. Okay, so this is called asteroid. It's not an asteroid in the sky, but we call it asteroid. Okay. Try to remember this parametric curve. Okay, when you have a positive number times cos of t, the whole thing cubed, and y is the same positive number times sine of t, the whole thing cubed. Now try to memorize the graph of that parametric equations, or the graph of the parametric curve defined by the parametric equations of these. Okay. So later on we're going to do some calculus on those curves. Again, for question 4, I did not give you the solution, the detailed solution, but I showed you the meaning. Okay. If you want, you can try to evaluate the points for all the t values listed. So there are too many here. You connect all the points, you can have the shape of the graph. Okay, in part 1, my intention is to show you some parametric curves. And then all the curves you have learned in past many years are called Cartesian curves. It's defined by an equation of x and y only. Now I'm trying to show you the relation between the two ways to define curves. One way is Cartesian curve, right? Defined using equations of x and y only. The other way is to use parametric equations. X is a function of t, y is a function of t. T is a parameter. Okay. Now we're going to talk about the relation between the two curves. In question 2, we are required to convert the parametric curves in question 1, 2, 3, 4, and 5 to parametric curves. Okay. I mean, I said something wrong. We are required to convert the parametric curves to Cartesian curves. So that's the nature of question 2. In this process, I want you to memorize some famous parametric curves, in particular the parametric equations representing circles. Okay, now look at question 1. Okay. For this one, I'm going to go over the solution to all the questions one by one. You look at question 1. In question 1, you have a parametric curve, or a curve defined by parametric equations. Now, to convert the parametric equations to Cartesian equation, we need to do something to cancel out t, right? To get a relation between x and y. So that makes sense? The only thing we need to use is the trig identity we have seen before. The trig identity is that cos of t, the whole thing squared, and then plus sine of t, the whole thing squared, is equal to 1. Okay. This is the only equation we are going to use to cancel out t, to get a relation between x and y. After that, you can identify the shape of the curve. Okay. That's question 1. Okay. In question 1, so maybe I'm going to copy the question, okay, so that it's easier for me to label something. X is equal to 2 cos of t, and y is equal to 2 sine of t. If you are not given a restriction on t, then we treat t as can take any real number. Okay. From these two equations, we can solve equation 1. So can I call that equation 1? Call that equation 2. Okay. We solve equation 1 for cos of t first. Okay. we have cos of t equals, again our target is to do something to cancel out t, so that we can get a relation between x and y, right? So cos of t is equal to half of x. You divide two sides of the equation here by 2. From equation 2, we solve equation 2 for sine of t. Okay. So sine of t is equal to, I believe it's half of y, right? And then I'm going to call this equation number 3. This is equation 4. Again, I mentioned earlier, the only trig identity we use to eliminate t, to get rid of t, so that we can get a relation between x and y, is that identity. Okay. So cos of t squared, and then plus sine of t squared. On one side, this is 1 for any value of t, right? On the other hand, now you look at it here, okay? Cos of t is half of x, so cos of t squared is x squared over 4, right? And then sine of t, the whole thing squared, is y squared over 4. Now you look at two sides of the equation. So this means we have an equation, now let's say x squared over 4, and then plus y squared over 4 equals 1. At this point, I guess many of you guys can see the shape of the curve already. Okay, but in order it's easier to see the graph of the function or the shape of the curve, I'm going to rewrite the equation to the following form. It's x squared and then plus y squared equals 4. I'm going to rewrite 4 as 2 squared. At this point, I guess many of you guys can tell me the shape of the curve. So what is the shape of the curve? So just tell me a term, please. Anybody? Anybody, please? Yeah, it's a circle. To tell me the circle, you have to tell me the center of the circle, the radius of the circle. Okay. Again, at this point, we are done question 1. Now we have a Cartesian equation, which is equivalent to the parametric equations. We are done the first part of the question. But now we are going to identify the curve. The curve is a circle. Okay, the curve is a circle. Again, to tell me the circle, you have to tell me two things: the center and the radius. Okay, it's a circle. I'm going to write it down. Okay, so this is a circle centered at the origin. Right? With a radius of 2. I know conic sections are not in high school, are not in BC high school curriculum anymore. But so this one is something you should know. Okay, so this is too famous. Again, the key thing is if you have this form, you have parametric equations. X is a function of t, y is a function of t. If you have that form, this is a Cartesian equation. Now the conversion from parametric equations to Cartesian equations is just you do something to cancel the t to get a relation between x and y. Okay. if you know how to do question 1, then question 2 and the question 3 so should be similar. Okay, I'm going to do question 2 in some more details. Okay, so maybe for question 2 I'm going to do it a little bit quicker. 3 plus 2 sine of t. Okay. I do not have to remember that. I can copy this into all the slides. Now I'm working on question 2. Okay, for question 2, the same thing. You solve that equation for cos of t. Cos of t is equal to, I believe you have x minus 3 on top, and then on denominator you have 2. I'm running a little bit faster. I hope you can follow. Okay. For this equation, you isolate t on one. You isolate cos of t on one side. Okay. You subtract two sides of the equation by 3, and then you divide two sides of the equation by 2. So you can have that. Okay. And likewise, sine of t. You isolate sine of t is equal to, I believe it's y. So let me know if you see anything wrong. Okay. You know I'm not super good at this. It's y plus 1 over 2, right? And then the way to cancel out the t is the same thing. You use the trig identity that cos of t the whole thing squared plus sine of t the whole thing squared is equal to 1. Okay. So you'll have x minus 3 over 2 the whole thing squared, which is cos of t squared, right? And then plus y plus 1 over 2 the whole thing squared. This is sine of t the whole thing squared. Okay. This is cos of t squared, and then plus sine of t squared, so the same as before. I wrote it kind of backward from the other question. So this is 1. Okay. So this equation is equivalent to, this Cartesian equation is equivalent to x minus 3 the whole thing squared, and then plus y plus 1 the whole thing squared equals 4. I'm writing 4 as 2 squared. Now, if you did not know, now remember, okay? So this is the graph of that equation is a circle centered at x coordinate of 3 and the y coordinate of negative 1, and the radius of the circle is 2. I'm going to write it down. Okay. The graph is a circle centered at the point with x coordinate of 3 and the y coordinate of negative 1, with the radius of 2. So we have done the conversion. We have done the conversion from parametric equations to Cartesian equation. In this process, I also want you to remember the shape of that parametric curve if you are given an equation something like this. So you see you can identify the center of the circle, 3, negative 1 from here. Okay. And the radius of the circle is given by 2. 2 is actually the coefficient of cos of t, or the coefficient of sine of t. So in order it's a circle, these two coefficients, they have to be the same. Okay. Any questions? Actually, it's simple enough, I think. If you you don't have any questions, we'll talk about the curve, the parametric curve in question number 3. If you did not know the Cartesian curve converted for question 1 and question 2, so probably you do not know question 3, but try to remember right now. Okay. In question 3, the first thing we do is to do the conversion. We're going to convert the parametric equations to Cartesian equation. I think you can see how we cancel the t, right? From equation 1 in question 3, you have cos of t equals x over 2, and then you have from equation 2 in question 3, you have sine of t equals y over 3, right? So you have let's say cos of t squared, so which is x over 2 the whole thing squared, and then plus sine of t squared, you have y over 3 the whole thing squared equals, now let's say cos of t squared and then plus sine of t squared, so which is 1. That's how we cancel out the t. Okay. Now this equation is actually equivalent to a standard form, some standard form. The standard form is as follows. Okay, x squared over 4, so maybe over 2 squared. I prefer to write 2 squared, and then plus y squared over 3 squared, so equals 1. Anybody knew this curve? So what is the graph of that function? Okay, the graph of that function is something like this. It's oval. I think we call 2 the semi. One of the semi-axis is 2. Okay, so you have 2 in here. So basically, you have a negative 2 in here. On the vertical axis, you have 3 in here, and then you have negative 3 in here. Okay, so the curve is kind of so in that shape. It's oval. Okay. Illustration only. Okay. If you want, I can show you the computer sketch, but I did not get this ready. So maybe I think it's not hard to tap. X is 2 cos of t. And the y is 2 sine of t, right? No, y is 3 sine of t, I think. Okay, it's oval, so ellipse, so however you call it. So just remember the shape of the graph. That's question 3. We do not get into too many details, but you just remember parametric equations can define way more complicated curves in many cases. I used to cover some more complicated curves, but in some sense, so they're not too important. I'm not going to do that this year. Okay. By that we mean I'm not going to cover too complicated parametric curves. But we'll do question 4. In question 4, actually the same idea. We're going to do something to eliminate t so that we can get a relation between x and y. That's how we get the Cartesian curve. Now in question 4, okay. In question 4, I'm going to call this one equation 1. I will call this one 2, okay. From equation 2, we solve equation 2 for t. So this one is simple. We just eliminate t, okay, so that we can get a relation between x and y. From 2, you solve equation for t, okay. We have t is equal to, watch me please. So t is equal to sketch is not part of the question, but my intention is to show you the graph of many parametric curves. So maybe I should have included that part of the question in the question, but so yes, try to know the sketch. In particular for question 1, question 2, and question 3. I want you to know the sketch for the parametric curves. Okay, from equation 2, we solve equation 2 for t. So t is equal to y minus 1, I believe, right? Y minus 1. I'm going to call this one. I do not have to give a name, okay. And then we plug it into equation 1. You see, it's kind of elimination, okay. Elimination. We try to eliminate t to get a relation between x and y, okay. We plug it into equation 1, so we have x equals t squared, which is y minus 1 the whole thing squared. Wherever you see t in equation 1, you replace t with y minus 1, okay. Minus 2t to y minus 1, right? At this point, we are done question 4. You see, I think from the stuff we learned before, you see it's kind of a sideways problem, right? A sideways problem. If you treat x as a function of y, okay. If you want to see the shape, actually I do not want to get into too many details. I will show you the computer sketch. On the right hand side, you have a quadratic function of y. You can see that, right? And x is a function of a quadratic function of y. So the graph of the function is kind of a sideways problem. Okay. For this one, I will show you the computer sketch. I hope this is the same one. I think that's the same one. Actually, on this website, I have to give a restriction on t. So how about I'm going to make t a little bit larger, okay? So now let's say so negative 100 to positive 100. I told you it's a sideways problem, right? So because after canceling out t, x is a quadratic function of y, so that's a sideways problem. You do not have to know You do not have to memorize the graph of that. Okay. So that's question number 4. I don't know what I did, but I lost this picture in my memory. I mean, in the computer's memory. We're going to complete the list. So to do question 5, okay, the same idea. From equation 1, you solve equation 1 for t, and then you plug t value of x into equation 2. I believe you see the answer already. So the answer is y is equal to t squared. T is x. So the Cartesian equation representing the parametric equations is actually y equals x squared. You know the graph of this function, right? A standard parabola facing up, right? So we're done this list. Okay. On this list in particular, I want you to memorize 2 parametric curves and the graph, and also the parametric. I want you to memorize 2 parametric equations and the parametric curves. Okay. So maybe question 1 and question 3. In question 1, it's the parametric equations representing a circle with the radius of 2. I believe if you replace 2 with any number a, you can represent the circle centered at the origin with the radius of a. Okay. And represented by question 3, I want you to know the graph of the parametric curve for oval. Okay. All right. So maybe question 2 is not too hard to identify the curve either. Okay. So just the 3, -1 will give you the center. 2 will give you the radius. Now we look at part 3. Part 3 is the conversion the other way around. By that we mean I give you the Cartesian curve. Represented by the Cartesian equation. Each of the 2 equations is called a Cartesian equation. Each of the equation is an equation of x and y, right? There's a way to convert the Cartesian equations to the form of parametric equations. Actually, that's how we can unify the two chapters. If you look at the textbook, simple, very simple. At this point, I want to mention how we can unify the 2 chapters. For any Cartesian, so later on, all the formulas for the arc length and also for the surface areas are given in terms of the parametric curves. And if we can treat a Cartesian curve as parametric curves, and then we can use one formula to handle 2 cases. That's the idea. I will make more comments later. Okay. Now let's do question 1 first. Simple. The idea is to treat one of the 2 variables x or y as a parameter t. I want to repeat. The idea is to treat one of the 2 variables x or y as the parameter t. In question 1, it's easy. we just treat x as the parameter t. Okay, so because y is a function of x, if you treat x as the parameter t, then the y as a function of t is going to be, so does that make sense? Y is equal to e to the power of t. If you do not see this way, you go backward. Go backward. By that we mean from these two parametric equations, if you cancel out t, you can get a relation between x and y as that, right? Y is equal to e to the power of x because x is t, right? That's how we can treat a Cartesian equation to be as parametric equations. You just set one of the two variables to be the parameter t. Okay. In this case, we do not have a restriction on t. Okay. By that we mean we treat t as a variable that can take any number. Now question 2. I think it's easy to see for question 2. Originally the Cartesian equation is x is a function of y. So this time if you treat y to be a parameter, it's easier, right? Now for question 2. Actually these two equations are the same. So just for question 2 I want to treat y to be the parameter. Okay, y is equal to t, and then x is equal to natural log of t, right? I want to repeat the two equations in question 1 and question 2 are essentially the same thing. I was trying to use the two questions to illustrate how to convert a Cartesian equation to parametric equations. You also know the graph of the functions, right? But that's not part of the question. It doesn't matter. That's question 3. Okay, now you look at the question on the screen. In this case, in the question we're trying to get the equation of the tangent line to a parametric curve at a point. The point is determined by t value of pi over 4. To get the equation of the line, we need two things. Now let's recall the thing we need in Math 101, in Calculus 1. To get the equation of the tangent line, we need a point on the line. Again, the point is determined by t value of pi over 4. You plug pi over 4 into equations, you have a point, right? Now the main thing is how to get the slope of the tangent line. The slope is a particular value of the derivative of y with respect to x. We learned that before. Recall Math 101. Okay. To get that, we need a formula for computing the derivative of y with respect to x. Okay. Now, there's only one formula you need to remember. The formula is the following. The formula is, now let's say you are given parametric equations. So now let's say x is a function of t as f of t, and y is a function of t as g of t, and both functions are so differentiable. It means you can get the derivative of the function on some interval. Now the formula, okay. The formula is that the derivative of y with respect to t, the derivative of y with respect to x, is equal to a fraction, the derivative of y with respect to t, and the derivative of x with respect to t. Of course, the restriction is that the denominator cannot be 0. Okay. Anything on denominator cannot be 0. This is the formula for computing the derivative of y with respect to x. In general, after applying the formula, the answer to this is a function of t. Okay, we can use that formula to get the slope of the tangent line. And by the way, the general parametric curves, it's kind of high school level math. Okay. Now the calculus part is the differentiation, integration. Whenever you have those things involved, you have university math, right? Okay. Now the solution. How about we get the slope first, the main thing first? Okay. In order to get that, we need to compute the derivative of y with respect to x. So this is the calculus part. Now the formula is, on numerator you have the derivative of y with respect to t, right? On denominator you look at the formula here. On denominator you have the derivative of x with respect to t. I will just do question 2, okay? And then if you know how to do question 2, question 1 and question 3 are simple. Actually question 3 is probably a question on the assignment. You look at y, okay? On the numerator you have the derivative of y with respect to t. For this one you have to use the chain rule, right? You have to use the chain rule. Now recall the chain rule. We spent a long time on chain rule when we did Math 101. I told you at that point, chain rule is used over and over again in different places. Now here's another place you have to use chain rule. Okay. To use the chain rule, you choose u so that y as a function of u is simple to differentiate. In this case, I believe you choose u to be sine of t. You keep u in mind, so do not write u. Okay. If using the prime notation, the derivative of the derivative of y with respect to t is 6 times sine of t the whole thing squared. So because your u is sine of t, you have 2 times u cubed, right? Differentiate 2 times u cubed, you have 6u squared. I said u, I write u in terms of t, okay? And because u is a function of t, we are differentiating y with respect to t. You have to differentiate sine of t, so which is cos of t. This cos of t is the derivative of sine of t. Okay, that's as far as we can go, I think, for the numerator. Now, the derivative of the denominator is the derivative of x with respect to t. So you have to differentiate the double underline with respect to t, right? The derivative of x with respect to t. For the same reason, it's 6 times. To differentiate dx over dt, you choose u to be cos of t, right? So you have 6 times cos of t squared. And then you differentiate cos of t, you have negative sine of t. Okay. If you have trouble with this, review the chain rule. Okay. I think we can cancel out something. 6 and 6, so can be cancelled, right? We can cancel out 1 sine of t. We can cancel out 1 cos of t. So please, double check for me, okay? There remains only negative. On numerator you have sine of t remaining. On denominator you have cos of t remaining. So do you have negative tan of t? Actually, you do not have to convert to tan of t. Okay. This is a function of t. This is not the slope we are looking for. Anybody want to tell me the slope? The slope at a particular value of t, the slope has to be a number. We need the number. Okay. So the slope is actually computed using the derivative of y with respect to x when t value. So because the point is determined by t value of pi over 4, right? So the derivative of y with respect to x when t value is equal to pi over 4. I said the meaning of the notation. I'm going to repeat. This notation, it means the derivative of y with respect to x when t value is pi over 4. This is a number. So you plug t value of pi over 4 into dy over dx. So you have negative tan of pi over 4. This trig value is so famous, right? Tan of pi over 4 is 1. So you have negative 1. This one is the slope of the tangent line. Okay. I'm going to write it down. Okay. So this gives the slope of the tangent line. So we have the slope. Now we need the point. Okay. Moreover, I don't know I can squeeze everything on this slide or not, but I'm going to write something here. Moreover, we need the point on the graph. The point is determined by t value of pi over 4. We just mentioned each value of t determines a point. Okay, this is the point determined by t value of pi over 4. Moreover, when t equals pi over 4, we have x equals, now let's say 2 times cos of pi over 4, the whole thing cubed, right? We have to compute this value. You do not have to simplify a whole lot. But cos of pi over 4, now let's record the trig values. I think cos of pi over 4 is equal to 1 over square root of 2 if you look at it. And the unit circle, I think many of you guys learn the trick with me. I rebuild trig using the unit circles, right? So cos of pi over 4 is 1 over square root of 2. So the x value when t value is pi over 4 is equal to 2 times 1 over square root of 2, the whole thing cubed. And also y value, I believe is kind of the same. Okay, y value is computed using 2 times sine of pi over 4, the whole thing cubed. this value is given by, I think, 2 times 1 over square root of 2, the whole thing cubed. Of course, it's possible to simplify. Can I remove the basic formula in here so I can write everything on one slide? So the point on the curve determined by t value of pi over 4 is the point with x coordinate. I will try to simplify a little bit, okay? So this thing cubed, you multiply the same thing 3 times. If I'm right, the x coordinate of the point is 1 over square root of 2. I will show you the details if you really want to know why, okay? And the y coordinate is also given by the same number, 1 over square root of 2. So this is the point on the tangent line. Okay, I will show you how I got this. Now let's try to compute 2 times 1 over square root of 2, the whole thing cubed. So this thing is 2 times 1 over square root of 2, and then times 1 over square root of 2, and then times 1 over square root of 2. You combine these two, you have 1/2, right? You have 2 times 1/2, and then times 1 over square root of 2. So which is 2 and 2 is cancelled. So do we have 1 over square root of 2? That's how I got the x coordinate and y coordinate of the point. Okay. So simple enough. Now we are ready to get the equation of the line. Okay, you have the slope, you have a point. The slope is -1. So the equation of the tangent line is y minus y coordinate of the point equals the slope. The slope is -1, right? And then times x minus x coordinate of the point. That's the complete solution to the question. Okay. So we're done question 2. If you can do question 2, so question 1 is simple. Actually, the curve is simple, okay. And also question 3 is probably a question on the assignment. I haven't decided yet. You do not have to do the question right now, okay. Now we move on to part 5. In part 5, we are going to talk about the integration part, okay. For this, for part 5, we are going to find the area of the asteroid, the weird asteroid. Okay. In this case, you imagine a value is 2. So because I had a sketch of the asteroid when a value is 2. Okay. I'm going to copy everything to the PowerPoint. For this one, so probably I'm going to set up the integral only, okay. And the detailed integration is in the notes. I'm going to make more comments. You look at the graph of the function. Now I'm going to remove the tangent line. Okay. So by the symmetry, the total area is equal to 4 times the region, the plane region enclosed by this portion of the curve and the horizontal axis and the y-axis. So by that we mean you look at the mouse cursor, okay? The total area is actually 4 times the area of that portion, the area under that portion of the graph when x is from 0 to 2, right? We'll set up the integral. We do not need too many formulas. We can just use the knowledge we knew before, okay? In this particular case, so maybe the solution key, I only set up the integral, okay? The total area, if I use A to denote the area, is 4 times the area from 0 to 2. In this particular, actually we are talking about the general case when A value, for any A value, okay? Actually, I had a typo in here. I'm going to replace this B with A. Again, the area is 4 times the area of the portion in the first quadrant, so which is from 0 to A. If the function is denoted by y, so can I just write y and then dx? It means we compute the integral of y when x is changing from 0 to A. I can show you what's going on, okay? When x is changing from 0 to 2, so you can write from 0 to half pi. You look at that portion of the curve, the area under this curve when x is from 0 to 2. When x is from 0 to 2, the area under that curve is represented by the integral of the function y. When the integral is on the interval when x is from 0 to 2. Okay. And then the idea is to convert everything to t. It's kind of a substitution, okay? We convert everything to t. You see, x is a function of t as, in this particular case, x is a function of t as a cos of t the whole thing cubed, and the y is a function of t as a times sine of t the whole thing cubed, okay? Now we want to convert the integral to a new integral of t. So it's going to be 4 times. Okay, everything is going to be in terms of t. So does that make sense? T value of 0 will give you the point. Will give you that point, the point with x coordinate of 2 and y coordinate of 0. And the t value of half pi will give you this point. In particular, t value of half pi will give you x value of 0, and t value of 0 will give you x value of 2. I'm trying to say t value of, I will write it so backward. Okay. x value of 0 will give you t value of, is determined by t value of half pi. And the x value of a is determined by t value of 0. Actually, you can plug t value of 0 into x value or y value. You can see what's going on. Okay. So the new integral in terms of t is going to be x is from 0 to a, so t is from half pi to 0. I hope it's not too weird. Okay. And then you replace y with a sine of t, the whole thing cubed. Of course, you have to compute dx. X is the underlined, so dx is equal to a times chain rule again, a times 3 times cos of t, the whole thing squared, not the chain rule. Okay. And then times negative sine of t. And dt. So dt, of course. You just get the differential of x. I'll put everything in. Negative 3 a cos of t squared. And then sine of t dt. Okay. Surprisingly, the integral is not too hard to evaluate. It's hard, but it's not super hard. I will show you what's going on from the notes. In the notes, I have the detailed calculation of the area in here. I showed you that screen actually. So do you see the area? We got this part, right? The area is computed using 4 times the integral is taken from x value of 0 to x value of a. You integrate y using the geometric meaning. You can see that is true. Okay. And then our target is to convert everything in terms of t. Okay. It's basically a substitution. This part is dx. You look at mouse cursor. So this part is dx, right? And this is y, right? Convert everything in terms of t. Simplify. You have something like this. I told you the integral is a little bit hard, but not super hard. The next step is to reduce the powers using one of the identities. Can I skip that? If you really want to know how to evaluate the integral, it's always in the course manual. Now it's easy to use calculus to find the area of the circle. So we'll do that right now. Okay. Now, for example, I don't remember if it's one of the questions on your assignment, but we're going to do this. It's quite interesting. For example, if we're looking for the area of a circle with the radius of a, so maybe this circle with the radius of a. Do that. Okay. Again, you imagine you do not know pi r squared, pi a squared in this particular case, but you know calculus. we can use calculus to easily get the area of the circle. Okay. Now the solution. Now consider the parametric curve. Defined by the parametric equations of, so now let's say, you remember I told you how to get the parametric equations of a circle centered at the origin with the radius of a. So we'll use that. Okay, it's defined by x equals, now let's say, a times cos of t. We have seen that, right? Y equals a sine of t. The circle is a circle when t is changing from 0 to 2 pi. Actually, it's a complete rotation. That's a circle. Okay. Now we are trying to compute the area of the whole circle. The circle is something like that, centered at the origin. The radius is a. Okay. The same idea as we mentioned earlier. The area of the circle is computed using can I only draw 1/4 of the circle in the first quadrant? So that's a, right? That's y value of a. Okay, so the area of the whole circle should be 4 times the area under the graph of that function when x is changing from 0 to a. I'm trying to write it's 4 times the integral from 0 to a when x value is changing from 0 to a. The formula is y dx, right? The geometric meaning of the definite integral is the area under the graph of the function when x is changing from 0 to a. So we just use that. This time with the parametric curve, it's much easier to evaluate the integral. Probably we have seen how to use the Cartesian curve to evaluate the area or the integral. But trust me, with the parametric curve, you are going to see it's much easier. Okay, so the same as before. So this is 4 times. Now we are going to convert the integral to a new integral of t. Okay. In particular, we replace y with a sine of t. That's y. So do you see the circled part is y? Y is a sine of t. And to get this, we have to compute dx, right? Now let's get dx. So this time dx is much easier. So dx is equal to, you look at the mouse cursor, x is a cos of t. So dx, you differentiate a cos of t and then multiplied by dt. Okay. So dx is the derivative of a cos of t, so which is negative a sine of t, right? So do not forget dt. That's dx. Negative a sine of t, then dt. Still, we have to figure out the lower limit and the upper limit. I will squeeze it here. It's easy to figure out that x value of 0 corresponds to t value of half pi. the same as before. Okay, and the x value of a corresponds to t value of 0. By that we mean you plug t value of 0 into x. Cos of 0 is equal to 1. Okay, so you have x value of a, and likewise a t value of half pi will give you x value of 0. So because cos of half pi is equal to 0, right? So the new integral is taken from when t is from half pi to 0. Simplify the integral a little bit. You switch the lower limit and upper limit, or some people say the lower bound and upper bound, and then you get rid of the negative sign, leave out the constants. I think the constant part is 4a squared. Now look at the mouse cursor. You have 4, you have 2 factors of a, you leave out 4a squared. You end up with the integral of sine of t, the whole thing squared. Okay, the answer to that will give you the area of a circle with the radius of a. Now, I guess you can remember the technique involved in here. You did your midterm, so not too long ago actually. So you have 4a squared. So what's the technique? I'm not going to go over this in very detail, but the technique is to reduce the power of sine of t, right? You use the identity that sine of t, the whole thing squared, is equal to half of 1 minus cos of 2t, and then the integral is taken when t is from 0 to half pi. I'll stop here.